Hey all, so this video is about the library of functions. Another name for these, and this is probably what I'll call them, is parent functions. And so they're kind of the most basic form of the versions of functions that we'll work with in this course. So this section kind of bridges 1.1 and 1.2. So at the end of 1.1, they're going to ask you to identify these by, it's kind of a matching thing, by name, by the graph. And then in 1.2, we're going to pick up domain and range. And these are great examples to do domain and range on. So the one-to-one and the picture, that part you're going to see in 1.1. Domain and range and interval notation. If you want that to make sense, you might want to watch the first part of 1.2 first, where I cover interval notation if you don't already know that. So we got these functions, and our most basic function possible is constant function. And this is where, remember, this f of x is kind of like a y. So it's just where y equals some number. And so what it is it doesn't matter what x I put into this thing. For this example, y is always 2. So if I put in -2, it stays 2, 0 it's 2, 2 it's 2. So the output is always 2, so we just get a horizontal line. Is the function one-to-one? Well, no, because remember our test for a function being one-to-one is a horizontal line test. So this would be a no. And then our domain is our x values. If you haven't seen the 1-2 video yet. And so it's all the allowed, anything I can put into the function is going to be domain, it's the x values. Anything I get out of the function, like which you would think of as y values, is going to be the range. So the domain is going to go from this thing, I can put anything in there. So from -infinity to infinity is how we would say that in interval notation. Again, check out the beginning of the 1.2 video if you haven't seen this before, which you probably have. And then the range is, in this case, the range would be 2, but for a general form, the range would be the constant c. And that little squiggly thing, I'll see if I can make it better on this side, is a brace. And so when we're indicating like a list of numbers or a single number, we use a brace. And like I said, for this particular example, we would say the range was 2, but in general, whatever that constant is. The next one up is the identity function, and so this is basically the same thing as a linear function, except it's just sort of the special case. So this is just like y equals x. So when x is 0, y is 0, x is 1, y is 1. So both sides are identical is kind of the deal. Is it one-to-one? Yep, because it passes the horizontal line test. What's the domain? All real numbers. So we'll say -infinity to infinity. Sometimes all real numbers is also indicated by kind of a bold R like that. This is what we usually use in this book though. And then the range, so the range goes from low to high. And so it can go all the way down to -infinity on this side and all the way up to infinity. So if we look at our y values, they're all covered. So that again would be all real numbers. The absolute value function, that's this one. This is one that I'm going to put kind of a star next to, and we're going to use this one a bunch in 1.5, and so it's one that I test on. And the reason is they're all useful functions, but some of them are easier to draw than others. So there's going to be 3, absolute value quadratic, and then the one coming up would be square root. I'll just grab that right here. It's towards the end. So those are the 3 that'd be really good if you could just be able to draw them, basically the graphs that they have here, from memory without having to like work at it too hard. I'll talk about that a little bit more as I go on. Absolute value equations, so that's those 2 kind of straight lines on either side. And you might remember with absolute values, like if I do the absolute value of 2, it's 2. If I do the absolute value of -2, it's still 2. So when I have a function like this, think y equals absolute value x, if I put in 2, I'm going to get out 2. If I put in -2, it's going to act like a 2. It's going to do the same thing it did on this side. So it's like our identity function, except this side of it's been folded up into the positive, because when I put in the negative numbers, it acts just like the positive side. And so we get this kind of traditional V shape. It's not one-to-one because it totally fails the horizontal line test, so we'd say no. The domain, I can put anything in, I can get anything out because the x's go forever. So that one's going to be all real numbers again, or negative infinity to infinity. The range on this one's a little different. The lowest this graph ever gets is 0. So if I do absolute value is 0, it's 0. But anything negative comes out of positive. So the bottom of my graph is going to be at 0. So I'm using a bracket, remember, to include the 0. And anything on the graph, if the graph is there, if I ask, sometimes people will go, if there isn't a dot, does it still count? Yeah, if the line is an infinite number of dots, so we want to include 0. And then our graph goes all the way to infinity, so we'll do infinity on that side. Quadratic. So quadratic is a squared function, and this one gets used a lot. This is our first kind of Kirby graph, and you can kind of see the table of values here that they're plugging in. What I was saying earlier about these couple and the square root are really good ones to have in your head, because like I said, those are the ones I'm going to test on, mostly just because they're small enough to stay on the graph. I don't have to put a big giant graph on the test. But you want to be able to draw this without making a table. So hopefully by the time you get to 1.5, you kind of have the shape memorized. And I'll show you what I do for it. We want to be able to pick it up and move it around, flip it upside down, and still copy the shape. So say I was going to draw it right here. And I don't want to think about, like, okay, this is 0, 0, because it's not 0, 0 anymore. It's shifted. So I want to figure out how to copy the shape. So it goes 0, 0, 1, 1, and then it goes 2, 4. So for me, I think, okay, it goes over 1, up 1, and I make a point, and then it goes over 1, up 3, and I make a point. So if I wanted to copy that shape down here, I just go over 1, up 1, make a point, over 1, up 3, and make a point. And then I just make matching points on the other side. And then there's my, what's called a parabola, or quadratic, shifted down and to the right. And this is what section 1.5 is going to do, is we're going to take these parent functions, these basic ones, and then take them and draw them, you know, upside down and somewhere over in, you know, some other corner. So we have to have a way of drawing those without being dependent on a table. So that's why it'd be really good as you're working through these, if you kind of pick up the basic shapes on these so that you can do this in 1.5. Also in 1.2 we're going to use them a little bit also. Okay, so then we have to do 1-to-1. So it is not 1-to-1 because it fails the horizontal line test. So that's a no. Domain for quadratic. They didn't show the arrows on this, but it does go on forever. And so domain is going to be, it can go all the way out to negative infinity, and I got values all the way out to positive infinity. So negative infinity to infinity. And then the range, so the lowest it goes is 0, and it goes up to infinity. So next up is the cubic, which just follows the squared, and it has a really different shape from the square. And what it's doing is, because when I put in a negative in a cube, it can come out a negative. So instead of getting that kind of U-shaped up here, I'm getting kind of the flip of the U down and then the U shape up. So this one is one that's like not fun to draw, and that's why I don't use it as much. They're using a half to kind of get the second point. The one I usually do on the board would be, you know, if it's 2, then this is 8. And you can see we're all the way, you know, we'd be all the way up here off the graph. So that makes this one a little bit harder to work with, where you have to start kind of busting with the fractions. But so that's your basic cubic shape, different from a square. X to the 5th would look a lot like this. It would be 0, 0, 1, 1, but then instead of 2, 8, it would be 2, 32. So it would grow faster. And likewise, with the quadratic, if this was x to the 4th, it would still have the same shape. 0 would be 0, 1 would be 1, but when I put in 2 instead of getting 4, I would get 16. So what I get is a steeper U. And that's the same for kind of any of the even, if it's x to the 6th, x to the 8th, any of those even power functions are going to make that basic parabola shape. And likewise, any of the odd functions are going to make kind of this cubic shape over here. Is it 1-to-1? Yes, this time it is. Domain, I can put in negatives, I can get out, I can put in positives, so that's an all real. And then the range on this one is also all real, because it goes down forever on this side and up forever on this side, so all the y values are covered. So that's going to be negative infinity to infinity. These next two are a bit trickier. These are not ones that I use a lot in terms of the graphing sections, but we will see them. They actually end up with their own section on graphing because they're fairly tricky to work with. So take this as just kind of an intro, and when we get to chapter, I think 3, these are going to come back. So we have the reciprocal functions. So instead of y equals x, we have y equals 1 over x. And so what that does is as x gets big, if x is 1, it's 1. X is 2, now it's a half. X is 3, it's a third. So this thing's going to get closer and closer to 0, but never actually be able to get there. Likewise, if you remember that we can't divide by 0, that's undefined. That means as I approach 0, weird stuff is going to happen in that it's going to get closer and closer, but I can never actually cross that axis. So that's where we're getting kind of this weird behavior up and down, and then this weird behavior off to the sides. And so there's a table here that kind of shows that. The important features are the division by 0 creates that what's called a vertical asymptote. And then this one's also going to have what's called a horizontal asymptote, and we'll see again more about those in chapter 3. But those are kind of the hallmarks of the reciprocal function. It is 1-to-1. The domain, I can put anything in except 0 because that would give me division by 0. So for the domain, I have to go negative infinity to negative infinity to 0. Sorry about that. I'm using a parenthesis because I don't want to include 0. Union 0 again to infinity. So that's kind of the hardest way ever to write not 0, but that's what we got for interval notation. And then the range is going to do the same thing. It's going to go all the way down. It's going to come up, not be x equals 0 or y equals 0 here because there's this kind of weird asymptote happening. So this is going to go from negative infinity up to 0. And then after 0, it picks back up and then goes forever up. So that's going to be union 0 to infinity again. Reciprocal squared. So this is a little bit different behavior because of the square function on the bottom. I don't get out negatives. Here if I put in negative 2, I get negative 1/2. But here if I put negative 2, I get negative 1/8. Or sorry, positive 1. Sorry, I read that as a cube. If I put in negative 2, I get positive 1/4 right here. Because that square is going to make all our negatives positive. So basically it's like this half of the graph has been folded up, and then the shape's changed a little bit because of the square. So 1-to-1, nope. It doesn't pass horizontal line test. It has this vertical asymptote, so x can't be 0. And this, it kind of looks like it's touching, but it's just getting closer. So it's never going to touch the axis. So for a domain, it's going to be all real numbers except 0 again. And then for a range, it's going to be from 0, but not including 0, because there's no way I can there's nothing I can, 1 divided by something can't be 0. So it can't include the 0, but that goes all the way up to infinity. And then our last couple are our basics on our root functions. So we have an even root, a square root, and an odd root, which is a cube root. Square roots, we never write it, but they are an even root. It'd be like there's a little 2 there. It's just implied. This is the third of the ones that you're probably not familiar with that would be beneficial to be familiar with. And again, we want to be able to just take the shape and pick it up and draw it over here like upside down and not have to think about the table. So my kind of way of memorizing this one is it's the inverse to the square one that I showed you earlier. It goes over 1 and up 1, and then it goes over 3 and up 1. So if I wanted to draw that starting here but upside down, I could go over 1, down 1, over 3, down 1. And then I've copied that shape over here. And again, that's exactly what we're going to do in 1.5. Little table, make it make sense. X is 0, y is 0, x is 1, y is 1. And when x is 4, square root of 4 makes the 2. It is 1-to-1. That is a yes. Its domain, I can't put negatives into roots, but I can put 0, because square root 0 is just 0. So I want to include the 0 with the bracket, and then that's going to go to infinity. And then for a range, it looks like its lowest point is 0, and then it goes up to infinity from there. It does it slowly, but it goes up. So that's going to be from 0 to infinity. And our last one is this cubic function. So this looks like this. And so the cube, again, I can take a cube root of a negative number, because for instance, if I say, what's cube root of negative 8? So this is asking what times what times what makes negative 8? Well, the answer to that is negative 2, because negative 2 3 times does make negative 8. So for the odd roots, we can have negative numbers in them, but for the even roots, we can't. They're going to be not defined. So this one, here's the table again. It's also the inverse, if you happen to remember those from 98 or 95, of our cubic function. It's also a complete pain in the ass to draw, and so I don't use this one very much, but it kind of goes over 1, up 1, and then over 7, up 1. It's that 2, 8, but in this case now it's 8, 2. So very wide function to try to draw using integers. So again, I don't use it a bunch, but there it is. Let's see, is it 1-to-1? That is a yes, because it will pass a horizontal line test. The domain on that, now this time I can put anything in I want, so that's going to be negative infinity to infinity. And then the range is going to be low to high. So it does go forever down. It does it slowly, but it is going to keep going further and further down. And it goes forever up, slowly again, but it does it. So our range is going to be from negative infinity to infinity.